So in 5.2, we're going to build on and continue the discussion we started in 5.1. So one of the last things we talked about last time was a Riemann sum, which is what we're seeing here. We're going to use the Riemann sum to define the definite integral. So if f is a continuous function on a closed interval ab, we divide the interval ab into n equal parts with width delta x, which has the formula b minus a over n. We let a equal x naught and b equal xn, with x sub I equal to a plus I delta x. So this is all that same stuff we did last time with the Riemann sum, and we construct our partition a of the interval AB. The endpoints of each interval are x sub I minus 1, x sub I, and then this is where it gets a little different. We're going to let x sub I star be any point in that interval. So not necessarily the left endpoint, not necessarily the right endpoint, just some point in each interval. Then we define the definite integral from a to b as the integral, and we'll talk more about this symbol, from a to b of f of x dx is equal to the limit as n goes to infinity of the sum as I goes from 1 to n of f x sub I star times delta x. So this looks a lot like the Riemann sums that we were doing last time. The only difference is now, instead of picking the left endpoint or the right endpoint, x sub I star can be any point in the interval x sub I minus 1, x sub I. If the limit exists as a finite number and gives the same value for every choice, or any choice of the sample point x sub I, we say the function is integrable on AB, and the value of the integral is the common value of the limit. So the key in this last sentence is, for the integral to exist, we must get the same number every time we do this, regardless of which x sub I is selected. So that means that the value of the integral does not depend on the x's that are sampled. So you get the same value always. All right. So let's talk a little bit about this new symbol. So our symbol looks kind of like an elongated script S, and this is called the integral symbol. So the integral symbol is right here, and the integral symbol always pairs with a differential. So whenever we have an integral symbol, so this, we always have to have a differential, and we'll talk about why these two things go together. But the first major reason is it tells us which variable we are integrating with respect to. So when we say dx, it means the integral is with respect to the variable x. So the symbol is read as the integral from a to b of f of x, and sometimes we'll put on the dx as well. So notice that the integral symbol is read in a very similar way to the summation symbol. So going back to this would be read as the integral from a to b of f of x dx. The summation is read as the sum as I goes from 1 to n of f of x sub I star. So we read these in a very similar way because they are related. Okay, so our first example is really just identifying some vocabulary. So for example 1, if we have the following integral, this is read as the following. The integral from 0 to pi over 2 of sine t dt. So we want to keep in mind what the definite integral represents. So when we introduced the Riemann sum last time, we were adding up approximating rectangles to find the area underneath the curve. And each time we did that, when we computed that sum, we always got a finite number if the limit existed. So a couple of important facts about the integral, the definite integral, and the integral symbol itself. So the first thing we want to take note of is that the definite integral is a number. And as we will discover, in certain circumstances, it is going to be the area underneath the curve. We'll make that more precise in a little bit. And the second one is that the variable in the integral is a dummy variable. And this is the same as with the summation. So if we had the sum as I went from 1 to 3 of I, that equals 1 plus 2 plus 3. Well, that would also be the same as the sum as n went from 1 to 3 of n, because I would put in n equals 1, I would get 1, 2, 3 again. So in the summation, the index behaves as a dummy variable. The same thing is true for definite integrals. So if I had the integral from a to b of t squared dt, that would be the same as the integral from a to b of x squared dx, which would also be the same as the integral from a to b of happy face squared d happy face. So the symbol that we use to represent our variable of integration is irrelevant. We will get the same answer whether we use t, x, happy face, or any other symbol. It's just holding a place to help us recognize what variable we're integrating with respect to. All right. Now let's talk about, well, what does the definite integral represent? So if we connect back to the Riemann sums that we were talking about last time, if f of x is greater than or equal to 0, then the integral from a to b of f of x dx is the area underneath the curve f of x in between a and b. So if I have a and I have b, the integral is this area beneath the curve. So this area is the definite integral. So when f is a positive function, that means when it's above the x-axis, the integral is the area underneath the curve. So now this begs the question then, well, what happens if our function isn't always non-negative? So if f of x has both positive and negative values as outputs, we define the area above the x-axis to be positive and the area below the x-axis to be negative. So if I have the integral from a to b, area that's above the x-axis, so here and here in between a and b, so the area above the x-axis is positive, and the area below the x-axis, so here, is negative. So then if I call this area A1, A2, and A3, the value of the integral is, so we have the integral from a to b of f of x dx is going to equal a1 minus a2 plus a3. So to calculate the value of the integral, we're going to add up the areas that are above the x-axis, and we will subtract off any of the areas that are below the x-axis. So one thing I do want to mention is we are talking about definite integrals, which means the area underneath the curve from a to b. Oftentimes the word definite is omitted, and so you'll just hear the value of the integral. We really mean definite integral, but people get a little lazy in their spoken word, and it happens in math books and a lot of things, so oftentimes the word definite is left off and it's just as integral. All right, let's take a look at our next example. So example 2, part A, wants us to rewrite this Riemann sum as a definite integral. So to remind us from our definition we had earlier, the integral from a to b of f of x dx was equal to the limit as n went to infinity of the sum as I goes from 1 to n of f of x sub I star times delta x, where delta x was equal to b minus a over n, and our partition x sub I was given by a plus I times delta x. So using all of these formulas, we want to identify our limits of integration, so our a and our b, and our function f. So the first thing we want to identify is the fact that we know our delta x is going to be this part, so that's our b minus a over n. So equating those two things, if we have 3 over n has to equal b minus a over n, what does that tell us about b and a? Well, it tells us that b minus a has to be 3. Furthermore, we know this, since this is our delta x, we know that it is also equal to this. So this gives us then that x sub I is equal to a plus I times 3 over n. Okay, so we've got a couple of pieces of information here. And we know these. So what are we going to do? Well, let's start substituting in what we know. So the first thing we want to look at is, well, what is our f of x? So in our definition, we replaced every input x with x sub I star, where x sub I star was something that was inside of our function. So we notice we have a 3i over n, a 3i over n. So this looks a lot like our x value. We're going to have x, we're going to have another x. But this doesn't look like 3i over n, but we have an I cubed and an n cubed, and 3 cubed is indeed 27, so this would be an x cubed. So our function f is starting to look like f of x is equal to x cubed plus x sine x. So there's our f of x. All right, so coming back to our x sub I, we need to figure out what our limits of integration are. So we have the integral, we don't know a and b. We do know our f of x is x cubed plus x sine x dx. And now we need our limits of integration. So to do this, we can plug in some different values for this. And so we know that our sum is going from I equals 1 to n. So if we put in 0, if we remember from our partition for last time, when we were talking about making our partition, x sub 0 is a plus 0 delta x has to equal our a value. And if we plug in n, x sub n is a plus n delta x, which should give us our b. So using that fact, we can calculate our a and our b values. So if I put in x sub 0, that gives me a plus 0 times 3 over n, which is going to imply that our a value is 0. And if we put in x sub n, we're going to get a plus n times 3 over n. Those reduce out, and we get 0 plus 3, which gives us 3, and that's going to be our b value. So we get the integral from 0 to 3 of x cubed plus x sine x. All right, so now it's your turn. So let's go ahead and take a look at our U-try, because I know these things can be a little confusing. So let's go ahead and have us work the following problem. So we want to compare this to our definition of the Riemann sum. So we identify our delta x out here as 1 over n. So then that gives us that delta x is equal to b minus a over n, which is the same as 1 over n. And then we have our x sub I, which we know is a plus I delta x, has to be the same as what we have inside here. So it's going to be 1 plus I over n. So we have then that the I delta x is this piece right here. So then that leaves for our equality that a has to be 1. Or we could just plug that into our formula and we'd get the same thing. If I plug in, if I have x sub I equals I, or 1 plus I over n, x sub 0 gives us 1 plus 0 over n, which is 1. And if we plug in x sub n, that gives us 1 plus n over n, which is 1 plus 1, which is 2. If each of these are our x sub i's, then we're left with our function being x squared ln x. So as an integral, we end up with the integral from 1 to 2 of x squared ln x dx, which would be the value, or our definite integral, on that interval. All right, so the next page in our notes has a whole bunch of properties for integrals and then some values for known sums. So our properties for sums, which we may or may not remember from pre-calculus, so we're going to remind ourselves really quick. We're going to need them. So we have the property of sums that if we have a constant and we add the same constant to itself, repeated addition is multiplication. So the sum as I goes from 1 to n of c equals n times c. Because that's just saying add c to itself n times, which is the multiplication problem n c. I have a typo in this next one. So that c that was on the inside shouldn't be there. So there was a typo, so let's fix that. So the sum as I goes from 1 to n of c a sub I is equal to, we can pull the constant out of our summation, so it's c times the sum as I goes from 1 to n of a sub I. The last property says that if we have the sum or difference of sequences in a side of a sum, that is the same as finding the sum or the difference separately for each piece. All right, and then lastly, we have some known values for sums. So the sum as I goes from 1 to n of I is equal to n times n plus 1 over 2. The sum of the squares of the first n integers is given by the formula n times n plus 1 times 2n plus 1 over 6. And the sum of the cubes of the first n integers is n times n plus 1 over 2, the whole quantity squared. All right. So now, armed with this knowledge, we are now able to work example number 3. So for example number 3, we want to evaluate this definite integral. So in other words, we want to find the area underneath this curve. So we identify our f of x, which is this piece right here. And we're going to set up our Riemann sum. So delta x is equal to b minus a over n. So that's 3 minus 0 over n, which gives us 3 over n. And then our x sub I is equal to a plus I delta x. So our a is 0 plus I times delta x, which is 3 over n. So we get 3I over n for our x sub I. So then our integral in terms of the Riemann sum, the integral from 0 to 3 of x cubed minus 6x dx is equal to the limit as n goes to infinity of the sum as I goes from 1 to n of f evaluated at x sub I star. So that's going to be 3I over n cubed minus 6 times 3I over n, all times our delta x, which is 3 over n. So this is our f of x sub I, and that piece is our delta x. So this is our Riemann sum for that. So if we can evaluate this limit, we will be able to find the area underneath that curve, x cubed minus 6x. So first thing we need to do is simplify this up a bit. So 3I over n cubed, if we start multiplying all of that out, so we have the limit as n goes to infinity of the sum as I goes from 1 to n. And then 3I cubed, 3 times 3 times 3 is 27. I cubed over n cubed is n cubed minus 6 times 3 is 18I all over n times 3 over n. And now we're going to distribute that into our parentheses. So we keep going. We have the limit as n goes to infinity of the sum as I goes from 1 to n. 3 times 27 gives us 81 I cubed. N cubed times n is n to the 4th minus 18 times 3 is 30 plus 24, so 54 I all over n squared. So now we want to use some of our properties. So by our first property, well, our third property up here, we can break that summation up into two different parts. So the sum of each of these is going to become, by this property, we're going to have the limit as n goes to infinity of the sum as I goes from 1 to n of 81 I cubed over n to the 4th minus the limit as n goes to infinity of the sum as I goes from 1 to n of 54i all over n squared. Okay, so we broke our difference up over the summation operations, and now our sums are indexed on I. So I is what's changing, n is fixed in the sum, n only changes in the limit. So then with respect to the summation, n is constant. So we can use this property to pull constants out of our sums. So by this property, we can then pull anything involving an n out of our sums. So we get the limit still as n goes to infinity. Pulling our constant 81 and our n to the 4th out, we have 81 over n to the 4th times the sum as I goes from 1 to n of I cubed minus, and we pull out our 54 and our n squared. Oh, I forgot my limit, so let me put that in. The limit as n goes to infinity of 54 over n squared, and then we have our summation as I goes from 1 to n of I. So now we have these sums as I goes from 1 to n of I cubed, and we have the sum as I goes from 1 to n of I. And both of those are in our known values for sums. And we have this value. So then this sum is going to be equal to this, and this, I did that backwards. This sum is going to be equal to this, and this sum is going to be equal to this. So we replace them with what they're equal to. And we have the limit as n goes to infinity of 81 over n to the fourth times n times n plus 1 all over 2 squared minus the limit as n goes to infinity of 54 over n squared times, this one is equal to n times n plus 1 all divided by 2. So now we've eliminated our sums by using our known formulas. We now need to evaluate these limits. So we're going to have to do some algebra on each of these. So we have our limit as n goes to infinity of 81 over n to the fourth. Well, if I square n times n plus 1, that's going to give me n squared times n plus 1 squared all over 4 minus the limit as n goes to infinity. Here, 2 goes into 54 27 times. So then we're going to have 27 times n plus 1 all over n squared. And I'm going to write my n squared as n times n, because then I notice the n and that n reduce out. So we need to simplify all of this out a little bit more. So let's keep going. The limit as n goes to infinity, and I'm going to write everything out kind of longhand once again. So 81 times n, because that's n squared, times n plus 1 times n plus 1. Put my 4 here, and then I'm going to put an n, because I have 4 of them under each of these. And then do something similar here. The reason I want to do that is it will make evaluating the limits a little bit simpler. So in this first part, those reduce out. And then if I focus on this piece right here, if I have n plus 1 divided by n, I can do term-wise division. That's 1 plus 1 over n. And I'm going to get the same thing here, a 1 plus 1 over n. And then the 81 over 4 just comes down. Minus, and I'm going to get the same thing here, limit as n goes to infinity of 27. And if I do my term-wise division here, n goes into n once, and then I have 1 plus 1 over n. So the reason we wanted that in this form is the same reason we did it when we first started evaluating limits. As n goes to infinity, 1 over n goes to 0, goes to 0, and goes to 0. So then finally, when we evaluate this limit, we get 81 over 4 times 1 minus 27. So finally, we can get a common denominator if we wish. So we get 81 minus 27 times 4 is 108. All over 4 gives us negative 27 over 4. So you might be saying, well, hey, wait a minute. Didn't you say we were finding the area underneath a curve? Indeed we are. Well, how can that be negative? Well, let's draw a graph and see what this looks like. So if we go back to our original function that we were finding the integral of, we wish to graph x cubed minus 6x. So we go x cubed, take away 6x, and we're only interested in this graph between 0 and 3. So let's go ahead and pick our window. We're going to make our x min 0, and let's make our x max equal to 3. And when we graph, we get a picture that looks something like this. So thinking back to the very beginning, when we defined these integrals, we defined area above the x-axis to be positive, and we defined area below the x-axis to be negative. So if we call A1 this area, the area below the x-axis, and we call this area A2, which is the area above the x-axis, we then would have the value of our integral, so the integral from 0 to 3 of x cubed minus 6x dx is equal to negative A1 plus A2. And that's why it ended up being negative. So that tells us, since it's negative, that there was more area below the x-axis than there was above. So the area in this red zone, A1, was bigger than the area in the green zone up here, A2. And if we add negative A1 to A2, we are going to get this value right here of negative 27 over 4. So the definite integral is the area underneath the curve, with the caveat that area above the x-axis is positive and area below the x-axis is negative. All right. So keeping that idea in mind, that integrals represent area underneath the curve, in this next example, we want to evaluate the integral by interpreting it in terms of area. So if I were to sketch this integral, I have the integral from 4 to 6 of 2 dx. All right, so let's draw a quick sketch. So 1, 2, 3, there's 4, 5, 6, and here's 2. So if I were to graph the integral from 4 to 6 of 2 dx, my function would just be a horizontal line between 4 and 6. So then, if I were to draw that figure, the integral is this area. Well, what is this a picture of? Well, it's a rectangle. And the area formula for a rectangle is length times width, or I'm going to use base times height. So then our base would be 2, and our height would also be 2. So then that gives us that our area is 2 times 2, which is 4. So the value of the integral from 4 to 6 of 2 dx is going to be 4, because it's a rectangle. Technically it's a square because its base and its height are the same. And the area of a square with side length 2 is 4. All right, let's take a look at our next one. So it's also worth noting before I do this next problem, I made that graph by hand, but I totally could have done that on my graphing calculator, right? So if I grab my graphing calculator, I am trying to graph the function. So this is my f of x is 2. So if I just put 2 into my calculator, 2, I want to graph 2, and then I'm going to go zoom back to my standard window. if I were to grab that picture, in terms of the integral, my limits of integration were 4 and 6, right? So if I mark those two values on my graph, so 1, 2, 3, 4, and 6, it shows me I'm doing the same thing. It's just not quite as zoomed in as a picture. So I have 2 and 2, so my area is going to be 4. So for this next problem, using our graphing device is probably going to be helpful. So we want to graph between 3 and 5, negative absolute value of x minus 4 plus 2. So if I go y equals negative, to get my absolute value, I go alpha in window, and absolute value is choice number 1. I have x take away 4 plus 2, and then I graph. So to help make this a little bit easier, I am going to change my window a little bit. So I'm going to go my window. I'm worried about the values between 3 and 5, so let's just go look at those first, and we might need to change our window again in a second. And let's change our y min to 0, and let's change our y max to, say, 4. And then let's scale it in 0.25s. So I get something that looks like this right here, and we want to find its area. So this is an example of a compound figure. So I've got a couple of different things. So I know this is 3 and I know this is 5. So the distance from here to here is going to be 5 minus 3, which is 2. And I have something like this. To find the corresponding y value, I could do y of 5 is the negative absolute value of 5 minus 4 plus 2. 5 minus 4 is 1, so negative 1 plus 2 gives us 1. So this value is 1 and this is 1. So we actually have two figures. So I have this area right here, A1, and then below it I have this right here, which we'll call A2. So the value of that integral is going to be each of those areas in this compound figure. So when we look at the triangle that's on the top here in red, its base is going to be 2. Its height, this distance, is going to be 1. So the area formula for a triangle is 1/2 base times height. So that triangle is going to have area 1, and then the area formula for the rectangle is the one that we did before, is just base times height, so that's going to be 2 times 1, which gives us 2. So then the total area, or the value of the integral, so A is A1 plus A2, which is 1 plus 2, which is 3. So the value of that integral is going to be 3. All right, the next one is for you guys. I'm going to send you back to work on this, and you're definitely going to want to draw a graph of this and recognize it as some kind of geometric figure. So we're going to want to draw a picture of this. So we grab our square root of 4 minus x take away 3 squared. And we're going to change our window up a little bit because we want to go from 1 to 5 this time. And if we graph it, we get something that looks like this. And so our perspective is a little off, but it turns out that it's a circle. So if I'm going from 1 to 5, I should probably do this, but we want to zoom, and let's change it to square. So we get something that looks like this, so it looks a little more circle-like. So we identify our geometric figure as a circle or a semicircle, and with center here. So that gives us our radius of 2, and our area formula for a circle is normally pi r squared, but we only have half of a circle, so it's 1/2 pi times our radius squared. So the 1/2 and one of the 2's reduce out, so we get 2 pi. So the value of that integral is going to be 2 pi because it's half of a circle. All right, so let's take a look at our next example. So the next one says, use this graph to evaluate the following integrals. So the first integral we want to work on is the integral from -5 to -3 of f of x dx. So that means we want to go from -5 to -3, and we want the area underneath the curve. Well, that's going to consist of these two regions, but this first triangle is below the x-axis and the second triangle is above the x-axis. So that means the area of this first triangle is going to be negative and the area of this second triangle is going to be positive. But we notice for those two triangles that they have the same base and height. So we have base 1 for each of them, and they have height 4. So then our area is going to be 1/2 base times height. So it's going to be, our first area is going to be -2 plus 2. So they are equal but opposite, so the value of that integral is going to be 0, right? Since we have those two triangles, one above the x-axis and one below the x-axis, so this is negative area and positive area, but they're the same magnitude, so -2 plus 2 gives us 0. All right, I'm pretty sure the next one is your u-try. So for your u-try, I would like you to find the value of the integral from 2 to 5 of f of x dx. All right, so to do the u-try, we're going to be looking over here on the right-hand side of our graph. So between 2 and 5, is going to give us this region right here. And we're going to note, since it's below the x-axis, it's going to be negative area. So we're going to have a triangle. So our area is going to be 1/2. Our base is 1, 2, 3, times our height is 1, 2, 3, 4, 5. So 1/2 times 3 times 5 gives us 15/2, or if you prefer as a decimal, 7.5. But then we got to be careful, since it's below the x-axis, it's going to be negative. So our correct solution is negative 15/2 would be the area, or the value of that integral. All right, so the next one is we want to find the integral from -3 to 2 of f of x. So continuing along the same thing, we want to go from -3 to +2 of f of x dx. Well, -3 to +2, well, that's going to be this part right here. And we have to be a little bit careful when we do this. It's a little tricky if we're not paying really close attention. This is actually two different regions. There's a rectangle right here with width 1 and height 4, and then it transitions to a quarter of a circle here with radius 4. So the area of the rectangle is going to be 1 times 4. So the area of that rectangle is 4, plus the area of a quarter of a circle is 1/4 pi times our radius squared. So in this case, 4 squared. So once again, one of the 4's reduce out, and we're left with 4 plus 4 pi. So the area of that region is going to be 4 plus 4 pi. The last one wants us to find the integral from -5 to 5. Well, that's the entire thing. Well, the integral from -5 to 5 is just going to be all of these areas that we found. So it's actually just going to be the sum of the answers to the previous three things. So the first part had area 0, so it's going to be 0, plus the area of our second part was what we just found here, was 4 plus 4 pi, plus the area of our last part, which was the part in green, which is -15/2. And if we combine all of those up, so 4 plus -15/2, that would be 8/2. Take away 15 would be -7/2, so we get 4 pi minus 7/2. And that would be the value of our integral. Because the order we add up the area in really doesn't matter, since we'd found the answer to each of those parts separately. The integral of all of it is just the sum of all the areas, so it's just the sum of all of the answers. And that actually leads into some of the properties that are listed next. So basically what this is telling us is that if we break up an integral into smaller parts, we can calculate those smaller parts independently. So let's take a look at some of our properties that are on the next page. So here are some of our properties of integration. So specifically, we have, if we have the integral from a to b of f of x dx, if we interchange the upper and lower limit of integration, so instead of integrating from a to b, we integrate from b to a, it's going to change the sign of the area. So if we reverse the order of the integration, it changes the area from positive to negative, or from negative to positive. The second one says that the integral from a to a of f of x dx has to be 0. Well, that should make sense, because if the width is 0, it doesn't matter what the height is. 0 times anything will always give us 0. Our next property says the integral from a to b of c dx is c times b minus a. Well, we actually did that earlier. That was exactly this one. It's saying that if we have the integral from a to b of a constant dx, that's just the area of a rectangle where the base is b minus a, so 6 minus 4 gave us 2, and then that would be the height. So this says that the integral of a constant is equal to the constant times the width of the interval, because that's just the area of the corresponding rectangle. Since integrals are defined in terms of Riemann sums, we can break up integrals over sums and differences. So the integral of f of x plus g of x is the same as the integral of f of x plus the integral of g of x. The next property says that the integral from a to c of f of x dx is the same as the integral from a to b of f of x dx plus the integral from b to c of f of x dx. Well, that's what we were seeing here. We actually used that property more than once, twice, because if we had the integral from negative 5 to 5, we said that that's the same as the integral from negative 5 to 3 plus the integral from negative 3 to 2 plus the integral from 2 to 5. So we have the property of integrals that says if we're trying to find the area underneath the curve, we can break it up into as many smaller figures as we need to in order to calculate that area. And lastly, we have the constant property of integration. So just like with derivatives, if you have a constant times a function, you can pull the constant out of the integral, do the integral first, and then just multiply by the constant. And so this is exactly the same as the property that we used when we were doing derivatives. Okay, so let's look at a couple more examples. So we have the following. All right, if the integral from 1 to 3 of f of x dx equals 7, and the integral from 1 to 3 of g of x dx equals negative 2, we want to find the integral from 1 to 3 of 6 g of x. So by our properties of integrals right here, our last one here says if we have a constant times a function, that this is the same as 6 times the integral from 1 to 3 of g of x dx. So that's 6 times, and the integral from 1 to 3 of g of x dx is equal to 2. So then we can just replace it with what it is equal to, which is negative 2. So 6 times negative 2 gives us 12. So the integral from 1 to 3 of 6g of x is going to be equal to negative 12. All right, so now your turn. All right, so to do this problem, we're going to use the property, the sum and difference property of integrals. So this is equal to the integral from 1 to 3 of g of x dx minus the integral from 1 to 3 of f of x dx. And we know that the integral from 1 to 3 of g of x dx is negative 2, minus the integral from 1 to 3 of f of x dx is 7. So negative 2 take away 7 gives us negative 9. All right, let's keep on going. So in our next example, we have the integral from 1 to 3 of f of x plus 2. So the first thing we'd want to do is break this up into our two separate integrals. So the integral from 1 to 3 of f of x dx plus the integral from 1 to 3 of 2 dx. So we know the integral from 1 to 3 of f of x dx is 7 plus, this is the integral of a constant. So that's going to be this property right here. The integral from a to b of c dx is c times b minus a. So it's that rectangle. So it's 2 times 3 minus 1. So that's going to be 2, and 2 times 2 is 4. So 7 plus 4 gives us 11. So the value of the integral from 1 to 3 of f of x plus 2 is 11. All right, so we have a couple more properties of integrals, and these are comparison properties. And if you think about them in terms of area, it will help some of them make a little bit more sense. So the first one is something that follows directly from our definition. If f of x is a positive function, then on an interval AB, then the integral of f of x dx on that interval has to be bigger than 0. Because if it's above the x-axis, the area has to be positive. The next one says, if f of x is bigger than g of x on the interval AB, then the area underneath f is greater than the area underneath g. Well, that should make sense if the heights are always bigger. So if the outputs of f are always bigger than the outputs of g, f is going to have more area underneath it than g of x. Similarly, if we have the absolute min and the absolute max of a function on the closed interval AB, then the value of the integral has to be in between the minimum times the length of the interval and less than the maximum times the length of the interval. This one really makes sense in terms of a picture. So imagine we have the interval AB and we have some function that looks like this. So this would be our min right here, and this would be our max. So what this is saying is that the area underneath that curve, so the area underneath the blue curve, is less than the rectangle in red, but it's bigger than the rectangle in green, right? Because it says if you take the smallest value of the function and make a rectangle, that has to be less than the value of the integral. If you take the largest value that ever comes out of the function and use that as the height of a rectangle, the integral has to be less than that. And the integral itself is trapped somewhere in between those two values. So in terms of a picture, that last one makes a lot of sense. All right, so let's go ahead and use these properties to estimate the value of this integral. So it says, use the comparison property to estimate the integral from 0 to 3 of 1 over x plus 4 dx. Okay. So we want to estimate this, so let's draw a graph. So if we just go y equals on our calculator, one over x plus 4, and we graph it, we get something that looks like this. We're like, well, we're not really interested in what's happening over here, so we want to specifically look between 0 and 3, and it looks like the height of our graph is really, really small between 0 and 3. So let's go window. Let's make our x min 0. Let's make our x max 3. We can leave our x scale at 1. Let's make our y min 0. Let's make our y max 1, and let's scale in 0.1s. So when we do that, we now get a graph that looks something like this. So we want to estimate the value of this integral. So the maximum value of this integral would be if we made a rectangle right here using the maximum value, which occurs at the left endpoint. The minimum value of that integral is going to occur if we make a rectangle using the right endpoint. So in both cases, we know that the width of this rectangle is 3, because that's 3 minus 0 equals 3, which is our b minus a. So then what is the value right here going to be? Well, the maximum value occurred at the left endpoint, so that's going to be f of 0. So f of 0 is 1 over 0 plus 4, and that gives us 1/4. And the minimum value occurred right here, which was at x equals 3, so that's going to be f of 3, which is 1 over 3 plus 4, which gives us 1/7. So then, by our estimation property, we have our m is less than or equal to f of x is less than or equal to m, so our little m is 1/7, our big M is 1/4, so it tells us that our integral is trapped in between these values. So we're going to have 1/4 times our b minus a, so our 3 minus 0 is less than the integral from 0 to 3 of 1 over x plus 4 dx, which is less than or equal to the maximum, I have a righto there. I even did the right color, but that's 1/7, which is less than or equal to 1/4 times the length of our integral, or of our interval, which is 3 minus 0. So simplifying, we get 3/7 is less than or equal to the integral from 0 to 3 of 1 over x to the 4th dx, which is less than or equal to 1 over 4 times 3, so 3/4. So then, if we check those, we have 3/7. So 3 divided by 7 gives us 0.42, and 3 divided by 4 gives us this. So those aren't very tight estimates, and as we saw from our picture, that we made. All we know then is that the area is somewhere in between 0.42857 and 0.375, or more precisely, that it's somewhere in between 3/7 and 3/4.